Okay. Thank you, Indo, for the introduction. And first of all, I'd like to thank the organizers of this conference, discussion meeting, school lectures, for the invitation to come here to India. It's my first time to this beautiful country, and I really enjoy the time here. And although the difference in temperature from my country to here is not the absolute value, but just 15 degrees or so, or maybe even 10, it's still a pleasure to be in this warm atmosphere. So my talk will connect, I hope, quite smoothly to what both Antoine said in the morning and what Rosa just told before. We will again be interested in Hunds coupling in multiband systems. That will be the overall setting, what we are looking at. And I will pick two examples of, there is some error, that this we don't want. Yeah, that's better. We will take two examples. That's a technetium compound and a chromium compound. And I will be interested in particular in what other instabilities can occur on the playground of these Hunds correlated metals, or correlations that appear due to Hunds rule coupling. So this is work that I've been doing the last 2 or 3 years together with Antoine and Yarnem Ravlet in Paris, and lately with Gianluca Giovanetti and Massimo Capone, who are both in Trieste at CISA. And funding comes from Austria, Vienna, and from Paris, from École Polytechnique. Okay, so you've seen this table of elements already quite a lot of times. And we learned already from Didi Sarma, for those of you who were in the school, that one could rearrange these things to get things there where they belong to be. But I will take a more conservative perspective and just tell you what you normally look at when you look for magnets. So when you look for magnets, you would stick to your 3D row. That are the magnetic materials that also what Didi Sarma told you. You have cobalt, nickel, you have iron here, manganese. So these are the things which show strong magnetism as elemental materials normally. So you go there. But what about these 4D and 5D materials? So you would say 4D materials, they have a smaller U, they have a larger bandwidth, the orbital overlap is bigger, so they should be less correlated. Correlations should not play a role. 5D elements should be vegetables. So I will not talk about 5D elements today. But you normally kick that out of the game. And then the same with these lanthanides. 4F should be very correlated, 5F to some extent. Now you would say, okay, correlated materials are 3D transition metals and their oxides, and 4F and 5F to some extent. And 4D transition metal oxides, ruthenium and technetium, they are 4D elements that should not be so strongly correlated. But we heard already in the morning in the talk of Antoine, in a very beautiful example, also agreement of theory and experiment, that the ruthenates indeed are correlated metals. They have an effective mass of 6, which is a factor of 2 larger than in the pnictides, which are 3D materials. So you have to compare these numbers. So they are strongly correlated materials. And we will see what technetium does. This will be the first part of my talk. I will show you what happens in this material. Okay, it's all about Hunds metals. So the important player that comes into the game here is the Hunds rule coupling J. And I think since we did not see any multiband Hamiltonian so far, for also the students of you, I will spend one slide on showing you the terms and showing you what U and J is. Okay, so we have the Hunds rule coupling in addition to the Coulomb interaction U that you have in a one-band model. And we learned in the morning that this produces systems with the small coherence scales. I will show you the data then on this ruthenium compound, what this small coherence scale really means, and small coherence temperatures. But what about the instabilities? What happens on top of this ground state that you have, which is a correlated metal, or very close to an insulating transition even? Okay, so the first thing I will study is this 4D T2G material, which is a technetium oxide, so it's strontium 2, technetium O3. And this is pure technetium. There is not a lot of experimental study going on this material because some of you might know this is radioactive and quite radioactive. So it's difficult to handle in the lab. It's very nice on the computer. That's good being theorists, so you can all do all this stuff. So there is a structural transition at 800 Kelvin at quite high temperature from an orthorhombic at lower temperatures to a cubic perovskite phase at higher temperatures. And you see this here in the X-ray experiment, that here between these, where do we have to go? Between 55 and 500 Celsius, that's here, degrees Celsius, you'll lose this peak, which is attributed to orthorhombic distortions. So here you're in the cubic phase, but then what happens later when heating it up even more, then this peak at lower energies, which here you cannot read this, but this is magnetic scattering, so nuclear neutron scattering. You have a peak that changes here between 500 and 750 degrees Celsius. So there is a magnetic transition at this temperature. And when you look then at the intensity of this peak here, they measure here the intensity of this peak, you can follow this in a kind of order parameter-like fashion, and you end up at roughly 1000 Kelvin. And 1000 Kelvin is a pretty large nail temperature for a transition metal oxide. So if you think of the manganese, so here we have strontium technetium O3, you have 3 electrons in 3 T2G bands. So you take strontium manganese O3, that's 3 electrons in 3 T2G bands, but in a 3D material. The nail temperature is only 260 Kelvin. So it's even below room temperature. The question is, why is this 4D element, technetium, supposed to be less correlated, that strong magnetic? Why is it such a good magnet? That's what we want to answer in the following. So this we do by applying our LDA plus DMFT scheme to this material. So there are very nice reviews on this. This is one of the first papers, but then there is a nice review by Carsten Held, and a review of modern physics by Gabi Kotlier on this whole method, so you can read all the details there. I just want to give you a flash of what you do. First, you describe your system, and that is then the system-dependent part by DFT calculations. There the system-dependent properties come in to some extent. Then we calculate the Wannier functions, that's also what Rosa was mentioning, and we continue with the DMFT calculation, including the correlated electrons. And here I wrote you the interacting Hamiltonian in a T2G system. That's a system with 3 orbitals. That's in this what's called the Kanamori representation. Don't bother about this, but we have a U which punishes 2 electrons in the same orbital with different spins. Then we have a Uj, which is the energy that you have to pay to put 2 electrons in 2 different orbitals. And then the Hunds rule J, it's exactly the energy that you gain by forming a large spin. So that's the low spin, high spin transition. That's the second Hunds rule of chemistry. For the chemists among you, in physics you write an Hamiltonian and then it looks like this. But it's the same picture. The DMFT, this picture you saw already, is a mapping of the correlated problem that we have at hand to an impurity problem. And Antoine told you in the morning that the impurity problem is still an interacting problem, so it's not a non-interacting thing that you can solve on the paper, but it's interacting, so you still have to apply numerical techniques, and we also use continuous time quantum Monte Carlo calculations for these calculations here. Okay, that's the method that we use. Now coming back to strontium technetium O3 and the comparison with the manganese compound, what we did is we calculated the true magnetic ground state. So we went to very low temperatures and let the system polarize in a G-type fashion. So you have spin up, spin down, G-type antiferromagnetism, and then you increase the temperature from very low temperatures. Here we went down to, that's maybe 50 or 40 Kelvin, and then you crank up the temperature and you see that the moment that forms goes down, and here is the nail temperature. To be honest, here we scaled the x-axis by a factor of 2, because in DMFT you have an overestimate due to the mean field nature of the moment formation. So the destruction of the moment is not 1000 Kelvin, but 2000 Kelvin, but that's a well-known problem of mean field theories, that they overestimate ordering temperatures. That was in this asymmetry broken phase, but still single-site DMFT. So there is no intersite self-energy, still a local self-energy. So when you do this for these 2 compounds, you end up with a nail temperature of roughly this 1000 Kelvin, given this factor of 2, for the technetium, and indeed a nail temperature of here it's 300 plus minus for the manganese. So the numbers come out, or at least the ratios come out very nicely. This is good, but still we did, as Mathieu said, we did the experiment on the computer. So we still don't understand. So we have data now. We have to understand. So we went further on and looked into the details of this. And then when looking at the band structure first and on the density of states, you see that there is a distinct difference, that manganese is here, has a bandwidth of roughly 2.5 electron volts, and technetium, being a larger atom, has strong overlap, and that's why the bandwidth is much larger. It's not a factor of 2, but it's quite large. So this is the first ingredient of an explanation of this larger nail temperature. So the W, the bandwidth, sets to some extent the global energy scale of your system. So that's the kinetic energy, the first approximation, and that is an energy scale in your system. So this is roughly a factor of 2 for the nail temperature. And temperature is nothing else than an energy. But then there is an additional factor of 2 that we have to explain. So still we are not at 4, we are at 2. And the additional factor of 2 comes from correlations. And correlations in the following sense. When you look at the manganese compound and you plot it on this kind of phase diagram where you put here the effective coupling is U plus 2J. I will come to this in a minute, why this is U plus 2J. And here the nail temperature, then manganese is here. And G equals to 1 is more or less the position where you have a transition from a metal to an insulator. That means manganese is very far in the insulating side. So the gap is 2.5 eV or so. It's a very clear localized moment insulator, antiferromagnetic insulator. Now the interaction values of technetium place the system here. So technetium is very close to the metal insulator transition. And if you follow these curves, so these crosses and axes are taking the black ones, for instance, manganese, and change interaction parameters. And everything falls on this curve. So this is a quite universal curve. This is the one-band Hubbard model DMFT result. You see, this is a quite universal feature. And strontium technetium 3 being at the verge of being metallic or insulating is at the top of the possible nail temperatures that you can reach in the system. That is an additional, if you look at the numbers, factor of 2 between magnesium and technetium. So summing all this up is 2 from the kinetic energy, 2 from being less correlated than the manganese compound, and in addition we saw that this is indeed also in real materials, not only model calculations, a hotspot for magnetism. So this is where magnetism can be strongest. And this information you might even use for what we call material design. So if you look for magnets who have strong, not strong magnetism, high nail temperatures, let's call it this way, you look for something that's not on this side, which is a very strong antiferromagnet, but you look for something which is on the verge of being metallic. So that is what we call material design, that you look at the calculation, try to use this information to look for new properties of new materials. Okay. What I wanted to say is also it's not a localized magnet because there are large charge fluctuations, and the moment at 0 temperature you can estimate from here, from this saturation value. Here it's not quite saturated, but you could say, okay, 3, which is the Bohr magneton times 3, the maximum value that you can reach for 3 electrons, so it will go here. So this is really a purely saturated localized system. This is not. And the difference between these two things comes from the charge fluctuations because it's close to a metal insulator transition. And this is not captured in a Heisenberg like localized moment description, this reduction of the moment. We have even a prediction that's related to the pressure dependence in the pnictides of this ordering temperature. That's the pressure dependence of the nail temperature in this oxide. For oxides, there is a phenomenological empirical law by Bloch, which is not the same Bloch from Bloch waves, it's some other Bloch. But he found empirically that oxides who are antiferromagnets and insulators follow this law. So if you change the volume, you apply pressure, change the volume, the nail temperature obeys this law, which if you translate it to something that you can understand means that if you apply pressure, the nail temperature goes up. And the amount it goes up follows this minus 3.3. There's even a number. And this is very well satisfied for many, many materials. Now, you know how this comes about. The more pressure means atoms get closer, there's more overlap, and the super exchange is T squared over U. So J gets bigger, and larger J gives you a higher nail temperature. But when you do this calculation in our scheme in LDA+DMFT, the nail temperature, it stays constant. And staying constant is a consequence of being on the top of this curve. If it would go down, then you have a Slater insulator. Then it has to go down. Being on the top of this means you increase the bandwidth a little bit, that would increase TNL, but you go down this maximum a little bit, it decreases. That's a subtle balance of up and down so that it stays constant. This could be done in experiment. If anybody dares to put his radioactive technetium in a pressure chamber, which I don't know, but this could be done experimentally and to show in what regime this system is. Okay. This picture you saw already. And the reason why this technetium compound does what it does is that it is in this regime. It is a half-filled system. So forget for a moment about this. It's a half-filled system. And we learned in the morning that adding the J to your normal U and increasing its value, the critical U goes down quite substantially here in this model calculation from 6 to 2 for a large enough J. And this is exactly what happens for this technetium. You might remember the strontium technetium 03 in the plot that Antoine showed. It was on the position where you have this metal insulator transition. That's exactly what happens. And the reason why it can be there at this point is J. It's not U. So the Hunds J gives you possibility to put this system into a correlated regime. And this delta, this is the mod gap, is U plus number of orbitals minus 1 times J. And in our case, it's 3. That's the U plus 2J, this effective interaction that I told you before. It comes from this analysis of the atomic multiplet of the atom. Okay, but now what happens if you go off half-filling and we take one electron out or we put one electron in? Here we put one electron in, and that's this, again, this example of strontium ruthenium 04. A well-studied system with still many surprises and many puzzles. And one of these puzzles that basically Jernej could resolve was the mass renormalization and the orbital dependency of this mass renormalization in this system. And again, it's the Hunds J that makes the difference here. If J is large enough, you end up here with 0.4. The mass of the XY orbital here is indeed close to 5, whereas the other ones are close to 3. So you get this mass differentiation through J. You could get the same masses of 5 by adding a larger U. But then the mass renormalization in all the orbitals would be the same. So it's really not the same effect. You cannot do either this or that. You have to increase J to get this differentiation. And then you have these 3 regimes in this calculation that at low temperatures, which is basically here, you have a Fermi-liquid regime below 30 Kelvin. Then you have a crossover regime where the scattering rate is larger than kT and you have deviations from T squared, so you have no Fermi liquid anymore. And then you have a completely incoherent scheme, regime where the scattering is linear in T. It's here, this flat regime. And that's also related to this how bad electrons, bad metals get good again that Michel told you. It's these energy scales that evolve as function of temperature in all these materials. And again, you see, you can go down to these temperatures here only due to CTQMC. I mean, the point that I could draw with Hirsch-5 would be here. I mean, it's not, it's here next to the wall. Okay, now we put 2 electrons into 3 orbitals. And we go back to 3D systems. So that's barium chromium oxide. And barium chromium oxide in a bulk has quite inconvenient properties for a theorist because it's not cubic. The tolerance factor is quite large, so it crystallizes in a hexagonal structure. And we want cubic structures because they are much simpler. In that sense, not so rich, but still much simpler to calculate. But luckily, recently there were experiments with thin films grown on STO, on strontium titanate, and they could stabilize thermodynamically stable perovskite crystal structures in tetragonal structure, so A equal B structures. And in addition, what they found is this thin film is insulating. So this is the resistivity as function of temperature, and you see nicely that it goes up for low temperatures and kind of diverges at very low temperatures. So this is insulating behavior. There were calculations in DFT which suggest that it's anti-ferromagnetic but slightly counted, so you get a small net ferromagnetic moment. But there is a strong tendency to this magnetic ordering. Just as a side remark, the other compounds like strontium or calcium chromium oxide here, they are to some extent cubic and bad metals. So they are in this bad metal regime. So the question was, we have now this barium chromium oxide, which is an insulator. Why is this guy insulating? That was our motivation to study this. And we first did DFT calculations. So you see again this very standard EG T2G splitting. So here you have T2G bands and EG bands, and the Fermi level is right here. That gives a filling of 2 electrons in these bands. Here is oxygen. This we forget. We do not put this into our model. If you use this system and do paramagnetic, so non-spin polarized DMFT calculations, you get this behavior that we saw already for the model calculation, that increasing U for a fixed ratio U over J does not give you something like this, which you would expect for a standard mod insulating transition, but you get this tail of quite a long region in U where you have a small C, but still not the mod insulator. It should be J over U, otherwise it doesn't make any sense. Yeah, it would be really small. No, it's J over U, yeah, you're right. I give you the number on the next slide then. So it's J over U, you're right. So indeed, this is another realization of a Hunds metal, at least in the calculation. But now it's not insulating, because the U that you would put and that we put is somewhere here. It's around 3 eV. It's a 3D system, so 3 to 3.5, this would be the value that you put for this chromium. So what we did is we allowed for lattice distortions. So we looked in this chromium. We knew that barium, or we all know that barium is big, so there is a strong tendency to distort this cubic lattice. We know from experiments, at least from this very rough X-ray data, that it's a tetragonal structure. So we have not a lot of freedom to change the structure. So we stayed into this tetragonal phase, and that what we did is we allowed for these kind of Jantella distortions. So we have this shrinking in this direction and increasing in the other direction. That's the distortion that we allow. Of course, we don't know if this is realized in experiment because we have no information. But what we did is we looked if this is, in this theory, a stable state. And indeed, this comes out. We did LDA plus U, or GGA plus U. And without this, without U, let's say, the stable solution is at zero distortion. If you add a U, then this goes down. So adding correlations on this Hartree-Fock level, on this mean field level, gives the tendency to this ordering. Yes? If you try to get the bulk system, it's hexagonal, yes. For this distortion? It's one of the possible distortions. I would not say, maybe there are rotations which are maybe more natural. If you have rotated distortions, yes. The thing why we use this is simpler. So we wanted to make a proof of the argument, so to say that distortions might drive this thing insulating. Of course, rotations of the octahedron might be the more natural choice, but then things get more complicated. So it was a technical reason.
May I just make a very quick observation? For completely different reasons, we were looking at a D1 T2G system on a substrate. Sorry, for completely different reasons, we were looking at a D1 T2G system on a substrate, and we did, by we, I mean my student, DFT plus U calculations, which included the STO substrate, which was undistorted. And we found that a small amount of rotations plus a distortion of the kind that you want to happen was perfectly okay for a system on the substrate when you include the substrate.
Okay, thank you. That's good for me. Yeah. Okay, thank you. Thank you, Andy. Yeah. 5 minutes. Okay, I'm almost done. So, of course, this is LDA plus U. So we want to, what we did now is we took a finite value of distortion, somewhere here around 0.1, around the minimum, and used this as an input for LDA plus DMFT to see if this also in DMFT gives us an insulator, because this is strongly biased towards the insulating solution. So if you allow for these distortions, of course you lift the degeneracy of the orbitals. So one of these xc, yc orbitals, which was degenerate before, is pushed up even above the xy, and the other one is going down below the xc. So of course you might expect what happens now. The thing is, it gets orbital ordered. So in DMFT, that's what we used, u equal to 3.25. I told you this value is quite natural. And j equals 0.5. By the way, this is more or less the constrained RPA value with some scaling from the strontium value, because the lattice is bigger. So to some extent, you can regard this as to be calculated. I mean, not to high precision, but at least calculated. Now what happens is that in LDA, including these distortions, you have a filling of xc.1 that's basically full, and these are not polarized, but on less than this 2/3 in this case. Now you add correlations, and this goes completely polarized. So here you have 1, here you have 1, here you have basically 0. So now you have a band insulator-like picture due to correlations. So you have two filled orbitals, one completely empty orbital, and you see that you have a gap of 0.3 electron volt, which is already very close to the experimental data. Yeah, 2, because you need 2 in 3 orbitals, yes. This is summed over spin already, so you have 1 here, and the third one is empty. The highest one is empty. So these correlations, they produce a huge correlation-induced crystal field splitting, because you see DFT alone is not enough. This is the DFT level, and correlations, they shift this even further, and you empty out this completely. This is filled. Now if you allow for magnetism, the thing that comes out is what you expect to follow good enough Kanamori. So we have G-type orbital order, so you get C-type magnetic order, and this is also the most stable state that we found. And indeed, it's almost fully polarized, so the up spin alone carries now 2 electrons. The down spin is basically empty. So you expect very strong magnetic moment in this system. If it's ordering or not, it's a thin film, so possibly not, but you should have maybe strong fluctuations in this system of magnetic type. And this, I hope, will be done next week or so, that you see it on the archive to some extent. Now, there are the conclusions. Since I'm, I think, done with my 5 minutes, I just let it there. I just switch to the materials. That's strontium technetium 3, which is half filled and therefore close to the metal insulator transition, proves to be a hot spot for magnetism, so it's 1000 Kelvin. And this picture of being on the verge of being localized gives an explanation for this. And in the chromium oxide, we have 2 electrons in 3 orbitals, small coherence scale. That gives rise to instability towards orbital ordering and lattice instabilities. So maybe one more sentence. This is a bit the chicken and the egg problem. So what we also did is, of course, you start with orbital ordering, with lattice distortions. You deform your lattice, then you already had some orbital ordering in your DFT because you shift your orbital levels. You can start from the undistorted lattice. In this case, you can get a solution, a self-consistent solution with orbital ordering in the undistorted lattice. So there is the general tendency to disordering also without the lattice distortions. So you can think of electrons repel each other, try to orbital order. The oxygen feels this, it relaxes a little bit. So this is a chicken and egg problem. What's first? First the oxygen goes away, or first the electrons repel each other and repel the oxygen. But it just means this system is very susceptible to this ordering type of things. And with this I want to quit. I think there's no more slide. Just these 2 packages, Trix and Wien2K, that we used for our calculations. And what you learned the previous week, and you will learn for the students of you next week how to use this. You will not do this calculation, but you will do a 1-band calculation. Okay, thank you for your attention.
Questions?
With the Hunds rule interaction, usually there is a pair hopping term. So what happened?
It is included. I just did not write it down on the slides. So it was, we used it in the fully rotational invariant form, which is possible in the three electron systems without too bad problems. Yeah. By the way, it makes a big difference in the case where you are off half filling. If you have a strong insulator, for the manganese compound, it doesn't make any difference if you have this spin flip terms at low energy in a case where there's a gap of 2 eV. So there it's not so important.
Yeah, one thing, follow up Andy's point, there's photoemission work for ultra-thin films of strontium vanadate on STO, and we've shown theoretically in a paper last year that it's Yarn-Taylor distortions on the surface, which actually drives it insulating.
Okay, that goes in this direction.
In the same direction.
Yeah.
And the other thing is, I'm surprised that you say that you need a localized, localized spin model description is not good for strontium technetium oxide, because what we did was we took LDA calculations, extracted J1, J2 in an extended Heisenberg model, and explained experimental data of the variation of the effective moment per site. I mean, if we treat it as a effective moment, we could get a very good description of all the experimental.
That's still one of these puzzles that's still not very good, well resolved for me, actually. Because from this picture, I would say it should not be valid. But I know your calculations. We did similar calculations, and the nail temperature is not so bad. It comes out. It has been used.
Not only the nail temperature, I'm talking about also the variation of the average moment per technetium site. There's experimental data, and we could get that within our calculation.
The average moment, you mean this reduction of the moment?
Yes, the reduced moment variation as a function of temperature, we got it within a class.
By
within a Monte
calculating
Carlo.
the magnetization on site in your model. Okay, this I didn't know.
Yeah, that's there in the paper.
I mean, this thing was used, there was one calculation in this picture of localized moment explaining the difference of strontium technetium-03, barium technetium-03, and then another one. But this has a subtle problem that they used the different crystal structures at very low temperatures for the explanation of different TNL. But at the nail temperature, everything is cubic. So you cannot use the angle as being a degree of changing in J, and then changing in J having this doesn't work. So that's why this is we can discuss this more later. But it's interesting that these different pictures give the same nail temperature.
So may I ask a more general question, and which I suppose I could have asked after Antoine's talk also. So you showed that a consequence of J is a differential mass renormalization, so that some orbitals may get a larger m star over m and other orbitals smaller. A priori, how do I know which one gets more and which one gets less? Is there a simple picture?
No. A priori, I think there's no such an argument. I know of no general argument to do this. I know from my experience that in many systems you get a larger differentiation with increasing J, but I think there is one, like the sulfide that Frank did, it's the opposite, no?
Maybe I can make a brief comment on this. So there are cases in which the perturbing field, if you want, that decides which orbital gets more renormalized is quite clear. So for example, in strontium-2 uranium-4, I think it's very clear that it is the proximity of the von Hove singularity for the XY band, which is responsible for the fact, ultimately, that the XY band is heavier. In other cases, I don't know, because I didn't look.
Yeah, because the effective coupling is small to the bath or to the surrounding. In other cases where you have more or less similar or many features.
Yeah. So I think the picture is that J promotes more independence, and then whatever perturbing fields you have around the differentiator orbitals takes over and triggers the difference.
Yes, Markus, this is very beautiful calculation, so I'm really impressed. I think they also trigger some general remark related to this nice Hunds phase diagram that we have seen a couple of times, this nice blue plot with the filling and the Hunds influence. So it really means that there should be a third axis, which is the orbital degeneracy, because in few of these oxides, the T2G states still remain threefold degenerate. So we have seen a couple of examples now with yttrium titanate being insulating because it's a one-band material, strontium iridate being insulating for that reason.
Yeah.
You have another example here.
Yeah.
So I think there is really a third axis.
We just
I
can't draw in
agree.
3 dimensions. So